In this refrigerator problem, we're going to use the coefficient of performance to figure out how much work is done. And the coefficient of performance is given by this equation when a refrigerator is cooling something off. Some books use a K or some other constant for coefficient of performance, but that's okay. It's QC over W. And first we have to figure out how much heat we pull out. We're taking water that's 20 degrees C. We're cooling it down. We have to pull some heat out to get it down to 0. We have to pull some more heat out to get it to turn into ice. We have to pull some more heat out to get that ice down to negative 10 degrees. So Q sub C, and I'll put the magnitude, the absolute values there. It's the mass times C for water times the change in temperature. That's going from 20 degrees to 0. And we're adding to that the phase change, right? We have to convert it from water to ice. And then we're adding to that the fact that we're cooling off. So this is the specific heat capacity for ice times delta T, MC delta T. So that's how much heat we have to pull out, cooling the water down, turning it into ice, and then cooling the ice down. So let's see, what does that leave us with? That's going to be 2 times 4190 times 20 degrees plus 2 times 3.34 times 10 to the 5th plus 2 kilograms. The specific heat for ice is 2090, and the temperature is 10 degrees, and that gives me a grand total 877,400 joules. And we know that the work then is going to equal that over the coefficient of performance. So we have to divide this by 4, and we get 219,350 joules for the work done. And basically, we now have the answer to part A. Part A says how much electrical energy does it take? Well, that's the work being done by our refrigerator, is the electrical energy that it consumes here. So that is the answer to part A, 219,350 joules. And part B says what is the heat that's being dumped into our room by our refrigerator freezer. And basically we use Q hot for that. And Q hot, some of these are negative, some of these are positive, so we usually put absolute values on here. The amount of heat dumped into our room is equal to the amount of heat that we pull out of our ice and water, and we have to add to that the amount of work that we did, the amount of electrical energy we used. And so we just add those two together. And it's 877,400 plus 219,350, 1,096,750 joules. And then in part C, they want to know the power. What's the power rating on our refrigerator? And power is work over time. So our work done is 219,350 joules. And usually we like joules per second. So I'm going to put, this is in 1 hour, right? That's how many joules were used in 1 hour, because we use the 2 kilogram number. That's 1 hour's worth of time. So that's 3,600 seconds, and a joule per second is a watt, and I get 61 watts. got to be careful with your W's here. We use W for work. Now we have a W for our unit, watts. Got to be careful with that.